Hello, and thank you for joining me in the first video on Year 13 integration for Edexcel's A-level maths. By far, well not by far, but it definitely is the biggest chapter. The differentiation was rather large. This is 2 sub-chapters larger. It is a huge chapter, and you need to be very, very brushed up and confident with the differentiation which has come before. So on that note, I've broke the mould and done something a bit different to what I normally would do with a warm-up. So I'm going to give you 6 to try, all on differentiation, to get you prepared for this next topic. So here they are. Question 1 is actually much easier than it seems. For question 1, in each box, you need to put each of these red options once and only once. So you should use each box here in each space. So there should be no options left. You can't use one option more than once. Some options are duplicated, which means that you don't need to duplicate them yourselves. Questions 2 through to 6 are purely differentiation. So it's a big warm-up, but I do believe it's worthwhile. Pause the video now, try these on your own, use your differentiation notes if you want to, and then press play when you're ready to see the solutions. Okay, assuming that's been done, let's have a look together at warm-up question 1. So you need to fill in these blank spaces in the statements below. So, since d by dx sine x equals what? All this is saying is, what does sine x differentiate to? We need to remember, or if you didn't remember, hopefully you've checked your notes and realised that sine differentiates to cos. So we put the cos x into this box. And then what we do is then think about the inverse. So because integration is the inverse of differentiation, then if sine differentiates to cos, then cos would integrate back to sine. It's going the opposite way around. Differentiation goes this way, sine goes to cos. Integration, cos goes back to sine. So perhaps you might think weirdly, in this box goes cos x also. Then what thing here would differentiate to negative sine x? Again, you need to remember that cos differentiates to negative sine. So cos goes here. So if cos differentiates to negative sine, that would mean that negative sine integrates back to positive cos. But what if I integrated positive sine? I can think about this as just balancing out this negative. If I were to multiply both sides by minus 1, then the derivative of minus cos would be positive sine. Therefore, if we integrate positive sine, we'd get negative cos. So in this box here goes minus cos x, like so. Part C should be probably a bit easier, less obvious, less easy to make a mistake rather. So differentiating the natural log of x. I've put the x in mod symbols here because when you're integrating, obviously you can only do the natural log of numbers which are non-negative, but greater than 0. So this mod symbol will come into use later in this chapter. But anyway, I digress. ln x differentiates to 1 over x. And so the short answer is just put 1 over x here. Therefore, integrating it, 1 over x would integrate back to ln of mod x. Plus, again, of course, always this arbitrary constant of integration of adding on here. And finally, very simple D, we've only got one option left. So e to the power x differentiates to itself, one of the key concepts of the exponential function. And then because integration inverses up, then if you integrate e to the x, you get e to the x. So 4 boxes, very, very easy, as long as you don't make any silly mistakes. Question 2. Find the derivative of x to the power n plus 1 all over n plus 1, showing all steps and working. I should have mentioned perhaps here that n is a constant. So if I were to just do this here, just by standard process, differentiate this, we need to remember that the power comes to the front, and then we take 1 off the power. And so the n plus 1 comes to the front, the power drops by 1, so x to the n plus 1 becomes x to the n, but of course we're still dividing by that n plus 1. Then you'll see the denominator has the same factor on the numerator. So I can divide through by n plus 1 on both top and bottom. So therefore, if I differentiate this weird thing, I just get x to the n. which is a nice way of showing that if we integrate x to the n, with respect to x, we get this standard result. X to the power n plus 1 divided by the new power plus the arbitrary constant of integration. Question 3. Differentiate tan x, showing all steps and working. Use a quotient rule. So what is the quotient rule? I'll just recap here. I'll put it in the corner for you. So if you want to differentiate a quotient, for example, a function u divided by a function v, then it's simply the product of the numerator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator, all divided by the denominator squared. And so what I need to do here is to rewrite tan as sine over cos. I can now use the quotient rule, which is, of course, just doodled this for you over here, just for a reminder. So, tan x, I've just called sine x over cos x. So now, applying the quotient rule, I leave the denominator as is and differentiate the numerator. So I'm going to get cos x multiplied by the derivative of sine x. Sine goes to cos. Then minus the numerator, which is u, sine x. And then I multiply that by the derivative of the denominator. If I differentiate cos, I get negative sine. And all of that is over v squared, which is over cos x all squared, which of course we can write as cos squared x. Now cos times cos is obviously cos squared. Minus sine times minus sine is positive sine squared. And of course that's still all over cos squared x. Then if you just remember a very crucial identity that cos squared plus sine squared equals 1, I can say that's 1 over cos squared of x, and 1 over cos is sec, and so 1 over cos squared is sec squared x. So if we differentiate tan, we get sec squared. That is to say that if we were to integrate sec squared, we would get back to tan. Question 4. Now we're going to differentiate cosec x, showing all steps and working, and again this is a quotient rule job. So cosec x, cosec is 1 over sine. So applying the quotient rule like we did for question 3, we take the denominator, multiply by the derivative of the top. If I differentiate 1, I get 0, so sine x times 0. Then minus, if I take now the numerator and multiply it by the derivative of the denominator, sine differentiates to cos. And then that's all going to be over the denominator squared, which is all over sine squared. So I'm just going to have minus cos x over sine squared x. Now I can partition this into 2 separate pieces here. And so what I'm going to do, I'm going to split this into minus 1 over sine x multiplied by cos over sine. Now minus 1 over sine is going to be negative cosec x, and cos over sine is the inverse of tan, which is, and cos over sine, of course, is going to be cot, so then I multiply by cot x. So we've got minus cosec x times cot x. So what this means is, if I were to differentiate cosec, I get minus cosec cot. Therefore, if I had to integrate minus cosec x cot x, I would get this back here. I'd get a cosec back. So what this implies is, if I were to integrate minus cosec x cot x, I would get cosec x plus c. However, What if I wanted to integrate positive cosec x cot x? Essentially, it's just adjusting this negative. So I'm just going to be multiplying by -1. Essentially, this is a slightly informal way of thinking about it, because you might be thinking c times -1 could be minus c. But I'm going to leave it as c because c is just any constant alike. So this is very sort of informal working, if you like. This is just thinking it through. So therefore, if I were to integrate positive cosec x cot x, or cot cosec as it's sometimes called, that'd give me cosec times -1, which is negative cosec x plus c. And that's what I would have put in this box if this box were as long as what I wanted to put in. Very silly of me, but there you go. That's just me being me, sadly. Question 5. Need to differentiate cot x, again, using the quotient rule as our hint. So let's rewrite cot x in terms of what it is in terms of sines and coses. Cot is the reciprocal of tan. Tan is sine over cos, so cot is going to be cos x over sine x. So we start by taking the denominator, sine x, multiplying by the derivative of the numerator. Cos differentiates to negative sine, so I get minus sine x there. Then I'm going to minus the numerator, which is cos x, multiplied by the derivative of the denominator. Sine differentiates to positive cos. And all of that, of course, is going to be all over the denominator squared, which is all over, therefore, sine x squared, better known as sine squared x. Now at the top, I've got minus sine squared, which I'm going to put into brackets, in fact, because I've got minus a sine squared x, and cos times minus cos is going to be a negative cos squared x. So it's minus sine squared and negative cos squared. All of that, of course, over sine squared of x. Pardon me. Now sine squared plus cos squared is 1, so this numerator will just become -1, just over sine squared x. 1 over sine is cosec, so 1 over sine squared is cosec squared. But of course, because it's negative cosec squared x. So therefore, if we differentiate cot and get negative cosec, what that's saying here is if I were to integrate negative cosec x, I'd get back to cot. But if I want to work out what the integral of positive cosec is, just taking care of these signs here, if negative cosec would differentiate to cot, then positive cosec squared would actually integrate to negative cot x. So we've got negative cot x plus c. Question 6. Find the derivative of sec x. Again, showing all steps in working. Again, use the quotient rule. So, got d by dx of sec x. Now, sec is just 1 over cos. So, applying the quotient rule, I'm going to differentiate. So, I'm going to take the denominator and multiply by the derivative of the numerator, which is just going to be 0, because 1 differentiates to 0. I'm going to minus off the numerator multiplied by the derivative of the denominator. Cos differentiates to negative sine. And all of that is going to be all over the denominator squared, which is cos squared x. So on the top, I've got -1 multiplied by negative sine. Minus times a minus is a plus, so I get sine x on the top, cos squared x on the bottom. And again, what I can do here is actually partition this out. So if I write, first of all, sine over cos, which is tan, I'm going to put sine over cos here. And then also, because I want another cos, I wrote this the wrong way around. I changed my mind halfway through. This is why I'm writing it back to front. So basically, I can think of it as 1 over cos times sine over cos. 1 over cos, of course, is sec. and sine over cos is tan. So therefore, if I integrate, again this box isn't big enough, so I'm going to just write it myself. If I were to integrate sec x tan x with respect to x, I would get sec of x plus the constant of integration. So 6 warm-up questions, more than usual, but I'm hoping you'll forgive me for thinking that your differentiation skills need to be brushed up and in good order, ready to tackle the integration which we're going to look at now. So here we go, let's introduce formally Year 13 style integration. Standard functions to integrate, first of all. So it's subchapter 11.1, so I'm not going to go dead hard straight away. So let's just think about what integration is. Well, as we discovered in Year 12, integration is a mathematical inverse of differentiation, and that's as simple as we often can get away with thinking about it. Of course, we need to also consider later on that integration can tell us the areas in between the x-axis and the curve, and other applications as well. But for now, we'll just start off with the basic premise that integration undoes differentiation. And some of the results in the warm-up we must know. So question 1 and question 2. Okay, so you need to know, for example, that sine differentiates to cos, and therefore cos integrates to sine. And the same for integrating cos x as well. Also as well, you need to know that the exponential function integrates to itself. And also, question 2, was that standard result if just integrating a polynomial function? So you need to know those two. But some integrals and some derivatives you're given. So question 3 to question 6 and some more you're given, which is good news. So I've said below, I'm going to put it on a different screen, but in the notes. Below, in the first column of this table I'm going to show in a second, is a list of all the relevant results found in the formula book. Now by relevant, I mean relevant to this chapter of integration, and also I suppose relevant to differentiation. So relevant results, I'm not calling the rest of the formula book irrelevant, I'm just saying what's relevant to the calculus chapters. So I'm going to give you a list of what's in the book, so hopefully that'll put your mind at ease to an extent. And also, treating differentiation and integration as inverses and adjusting the constants, what we can do here is consider the formula book results in a more standardized way, because the formula book gives some results as derivatives and some as integrals, but we can consider them all as derivatives or all as integrals. I'm going to show you what I mean now. So in the formula book, when it comes to the calculus, we've got 2 main sections. So this is just screenshotted rather, from the formula book. So the first bit is this result of derivatives. So these are the functions of x, these are the derivatives. And of course, we're including the constants as well. So we differentiated tan of x in the warm-up to get sec squared, and using the chain rule, tan kx goes to k sec squared kx. We've seen some of this in chapter 9 for differentiation. The formula book also goes on, therefore, after this to talk about integration and gives this little section here, where if these are your functions to be integrated, and these are the integrals. So, I don't know if it's just me being a bit strange, perhaps so. I found it slightly perplexing at times, where you're given some which are derivatives, some which are integrals. So just for consistency, let's think of this first of all as derivatives. So on the left is what's to be differentiated, on the right is what we get when we take the derivative. So this arrow just means from left to right we're differentiating. So the first one we can just add in. Tan goes to sec squared. The next one, we're told that sec kx goes to k sec kx tan kx. So this first section isn't going to be changed. So just adding all this in. So sec kx differentiates to k sec kx tan kx. We've got cot kx, which differentiates to negative k cosec squared of kx. And then cosec of kx differentiates to minus k cosec kx cot kx. Next, we've got a table in the formula book of integrals. So we want these as derivatives. This first one here at the top, let's just focus on this. We're saying that if we integrate sec squared, we get 1 over k tan kx. But this here in yellow is the exact equivalent of this line here. What this is saying is, if we differentiate tan kx, we get k sec squared kx. Therefore, going the other way, if we were to integrate k times sec squared kx, we get tan kx. But if we just wanted to integrate sec squared without the k attached, we have to divide through by k. So then we get sec squared kx integrates to 1 over k tan x. But because we want all these as derivatives, and we've got the derivative of tan x anyway, we don't really need this line here, because it's given to us in this first one already. However, here this is useful. Look at the ln of the mod of sec kx. That is what we get, 1 over k of it, by the way, if we were to integrate tan kx. Therefore, if we integrate 1 over k ln sec kx, we get tan kx. Therefore, adjusting the constant, multiplying both bits by k, if we integrate ln of sec kx, we get k times kx. K times tan kx, I mean to say. Similarly here, this way, going from right to left now, if I multiply both sides by k, ln of sine kx will be k cot kx. And this next one here, these are identities, and I might show this in either a lesson or another video. I'm not going to get into it now, but essentially, this here is an identity of that. So what we can do, if we multiply by negative k here for this first one, I can see that if I were to integrate ln cosec plus cot, I'd get minus k cosec kx, like so. But this other one here, because this 1 over k is all positive, if I go from right to left, multiplying by k on both sides, I'd see that if I were to differentiate ln tan of half kx, I'd get k cosec kx. And finally, the last line, in a similar how I've explained the others, multiplying both by k and going from right to left, if I differentiate the natural log of sec kx plus tan kx, I get k sec kx. And similarly for this one, that's an identity as well of sec plus tan, then I'd get this final result as well. Essentially, these results are given to us, is what I'm trying to show you, but thinking of them all as derivatives might be more useful, as might be if you think of them all as integrals in this next section here. So this is overkill. I'll just explain. Why am I doing this? It's because I'm trying to just enrich you with the confidence that the formula does actually tell you a lot if you know how to use it. It's not just reading it, it's knowing how to use it and applying and understanding the formulas in there. I'm hoping this will benefit in this understanding, talking it through here. Anyway, all as integrals. So looking at the top here, this top bit here is the derivatives. To integrate, I want to go the other way around. I'm going to go from right to left. So what about integrating, for example, sec squared kx? If I integrated k sec squared kx, I'd get tan kx. But because I just want to integrate sec squared on its own, I don't want that k, so I have to divide both sides by k. So therefore, integrating sec squared kx would give me 1 over k tan kx, which I can actually see in this line here as well. So just understanding the equivalency of these two, and I need to put in the arbitrary constant of integration each and every time here. The next one, integrating sec kx tan kx and adjusting for that k. Integrate sec kx tan kx gives me 1 over k sec kx plus c. Then this one, if I were to integrate negative k cosec squared x, I'd get positive cot kx. So if I wanted to integrate positive cosec squared on its own, that would give me minus 1 over k cot x plus c. So we get this result here. Then this bottom line, if I wanted to just integrate cosec kx cot kx without the minus k, adjusting by dividing by minus k, I can see that if I integrate cosec kx cot kx, I would get minus 1 over k cosec k of x plus c. And this final bit, we can just add on without any adjustments. So this next bit, integrating sec squared, gives me 1 over k tan kx, which we've already got from the above. So the next one, if I were to integrate tan itself, that would give me 1 over k sec kx plus the arbitrary constant of integration, and just following on these results as so. So cot kx, cosec kx, version 1 there, and version 2 using the other identity, and finally sec x, version 1 using that first identity, and then version 2 using this form here. So again, this isn't anything I've created, this is all given to you essentially. So use the formula book wisely, but don't just think of it's on the formula book, it'll be fine. Remember, you need to understand it as well as just reading it. That is the main thing by far. So, now I've laid the groundwork, let's actually do some proper integrating. So we'll say goodbye to the standard functions for now. And now I just need to mention another point. So, about what I've just shown you. Knowledge of those functions is really beneficial, as sometimes a question they expect us to be able to integrate by inspection. And what I mean by inspection is it just means that the examiner will be requiring you to adjust the standard results when constants are involved. So for example, the main constant was k in that table just before. The table above, if you've got the notes in front of you. So let's use those results. I'm not going to show you them again. They're yours to refer to if needed. Try to refer to them less and less as time goes on. So, a few worked examples. So, let's find the following integrals. So the first one. So, what I'm going to suggest here is we can think of integrals done in pieces. So this one, that's the same as if I integrate 3 sine 2x dx and then integrate 4 over x dx. And then we're to integrate minus the square root of x, which is obviously x to the half. Put it in index notation. So then, set of constant to the outside, I've got 3 lots of sine 2x dx. This bit, I've got 4 lots of 1 over x dx. And here, if a plus and minus is confusing you, what you can do, if I'm adding a minus, I can take this minus to the outside if you'd like. So I can say this is just minus the integral of x to the half dx. So let's just piece these together. If you need to have a look back at the formula book or above in the notes, the standard results, please do. But by the end of the chapter, you need to hopefully have these partially memorized, ideally fully. So what does sine integrate to? Well, sine integrates to negative cos, and we need to divide by this constant 2. And so this bit here, we've got 3 lots of, and then we're going to have minus a half cos 2x. So when I integrate sine 2x dx, I'm just going to get this. And then I've got 4 lots of the integral of 1 over x dx. We need to remember that when you integrate 1 over x, it goes to ln of mod x. So this bit here, 4 lots of that means 4 lots of the natural log of x. And finally, integrating polynomials, fairly easy. I'm hoping you'll agree, or hopefully remember if not, that you add 1 to the power, so 1/2 becomes 3 over 2, and we divide by the new power. So it's that divided by 3 over 2, but if I'm divided by 3 over 2, it's the same as multiplying by 2/3. And of course, you need to remember the constant of integration, which is often just given as a plus c. So simplifying and piecing these bits together now, so that bit there becomes that bit. We've pretty much got it done. So we've got minus 3 over 2 cos 2x, or minus 1.5 cos 2x, plus 4 lots of the natural log of x, minus 2/3 x to the 3 over 2, plus, of course, the constant of integration, c. Part B looks very, very confusing, and what I would say to you is, if a question looks impossible and you've revised and studied hard, it probably is, unless you're missing a little hint, trick, or manipulation. And this is one where we need to manipulate the sine over cos squared x into different components. And so what we can do here is just think about what this is in terms of simpler trig functions. So I'm going to rewrite this sine over cos squared x as just simply sine over cos multiplied by 1 over cos. So this bit equals this, and then I'm going to minus off the integral, and it's put dx, almost forgot. I need to minus off the integral of e to the x dx. Now sine over cos is going to be tan x, and 1 over cos is going to be sec x. What I'm going to do, I'm going to rewrite this not as tan times sec, but as sec multiplied by tan. It doesn't particularly matter in terms of the value of it, but it will hopefully help you, if you write it in this form, to identify what standard result we're going to use. So this bit here, I'm just integrating sec x tan x with respect to x. And so essentially this bit here, I've just rewrote like so. And I'm going to minus off the integral of e to the x dx, which I can just leave as it is. Now from the standard results, sec x tan x is one of these. And if you're not sure, have a look back at the table included in the notes or the formula book. But we need to identify that sec x tan x is a standard integral, and that will integrate to sec. So sec x tan x dx will just integrate to sec x. Then we've got minus the integral of e to the x, and e to the x integrates to itself. So that just stays as e to the x, then of course plus the arbitrary constant of integration. And so for part B, we've got that result, and I'll underline part A as well, because to be honest, I forgot to do that, and I do like underlining. Part C, this is a definite integral. We've got limits of integration here. Before I deal with the limits, I just want to neaten up what's inside the integral. So if I just forget the limits for a second, just consider this in an easier way. So I've got this here with respect to x. As it stands, I couldn't integrate that. I really couldn't. What I'd have to do is split it up into separate fractions. So I can rewrite this as 3x over x, which is just going to be 3. And this one here, I can split into plus 5 over x, with respect to x. If you're not sure we've got the 3 form, that's because 3x over x is 3, and then plus 5 over x, I have 5 over x like so. So integrating 3 with respect to x, that's going to be 3x. Integrate this, take the 5 to the outside, because it's a constant. I got 5 lots of 1 over x. 1 over x integrates to the natural log of mod x. And of course, we've got the plus c. So therefore, knowing that, if we're integrating from the limits of 5 to 3, of 3x plus 5 over x dx, we're essentially putting in 5 and 3 into this expression here, 3x plus 5 ln mod x, between the limits of 5 and 3. So I normally just deal with the indefinite integral first, okay? So I then get, of course, this result, and then I can put in the definite limits afterwards. So that's the last thing for me to do now. And so when x is 5, 3 times 5 gives 15, then this becomes 5 lots of ln mod 5. But because 5 is obviously positive, I don't need to actually say that that's mod 5. I can just put 5 ln 5 in. And then I'm going to subtract away 3x plus 5 ln x when x happens to be 3. So 3x becomes 3 times 3, which is 9, then plus 5 lots of ln of positive 3. So simplifying this down, 15 minus 9 is 6, and then I've got plus 5 lots, so I'm going to factorise out the 5. I've got ln 5 here, but if I'm minusing 5 lots of ln 3, I just need to conclude in brackets minus ln 3. So that's the next step, and then we're pretty much done. So one final step to simplify, reminding ourselves of the laws of logs. I've got 6, of course, then 5 lots of ln 5 minus ln 3. Both are to the base e, so both are to the same log base, so I can combine these using the laws of logs into ln 5 divide by 3. So I've got 5 lots of ln of what 5 over 3 is. So these are fairly standard type integrals. What examiners have now done is introduced a different type of integral since when I was doing my A-level maths. So I'm going to explain these in a bit more detail now. So what do I mean by new style integrals? This is just my phrase for them. It's not particularly recognised outside of my own head, but I do swear this is definitely a thing that's happened. And teachers by and large do agree with me, although I might not call them new style integrals. So what am I babbling on about? Well, essentially it's the calculators that are to blame. So because scientific calculators now are so sophisticated, examiners have had to rethink the way some calculus questions are phrased. So for example, in worked example 1C we did, modern calculators would be able to calculate the definite integral, but the answer would be given as decimals. So the examiner gets around this often by asking you for a definite integral in exact form, because the calculator will spit out a decimal. I'm going to show you how the calculator can work as a checking tool in a moment. Another way the examiner can almost force you to prove you're not just mindlessly using your calculator, but to know what you're doing. They'll ask you to also show working sometimes, but more common than that, what they've done now, which I think is rather clever, is now they ask you what the limits of integration are themselves. Whereas when I was doing my levels, we'd tell you the limits of integration, then you just have to compute it without the calculator often. But now, because the calculator is so powerful, this is a way of just flipping the question, if you like. So I'm going to give you 2 examples on these. So worked example 2. Given that k here is a positive constant, find its exact value, given this information here. So we're told the integral of 2x plus 1 all over x between the limits of 3k from k has to be ln 12, so therefore what is k? So let's just think about this without the limits for now. So what would the integral of 2x plus 1 all over x be? This in a way is quite complicated, so let's split this into separate fractions. So I've got 2x over x plus 1 over x, all with respect to x. So obviously that'll cancel. So I've got the integral of 2, which is going to be 2x, integral of 1 over x, which will be ln of x, mod x rather. Then of course I've got the plus c. So therefore, using this bit of information, essentially this is the main bit here. When we input the definite limits, the concept of integration doesn't matter, it essentially cancels itself out. We're just going to input 3k and k into this expression here. So therefore, the integral of 3k to k, 2x plus 1 all over x with respect to x, that's going to be 2x plus ln mod x in between the limits of 3k and k. And of course we know what this is. We're told it needs to be ln 12. So if we just input the limits into this now, so when x is 3k, 2x will become 6k, and then ln x is of course just going to be ln mod 3k. Because k is a positive constant, In fact, we don't need these mod symbols, in fact. So what we can do, if you leave them on there, it's not such a massive issue. But technically, because it says it's a positive constant, what I can do is just think of it as just ln 3k. And I'm going to minus off the lower limit. So when x is k, 2x is of course 2k plus ln. It's going to put mod k. Force of habit, just leave it as ln k. So then, if I simplify this down, 6k take away 2k is 4k, and then ln of 3k minus ln k. If you just remember the laws of logs, remember ln a minus ln b equals ln a over b. So in our case, with our a being 3k and our b being k, this will become ln of 3k over k, so the k's will cancel. We'll just have plus ln of 3. And we're told that needs to be equal to ln 12. Okay, so we've integrated it in between the limits. We integrated this, and we've got this expression here. Now all we need to do is just simply solve it to work out what k is in terms of ln of 3 and 12. So what I'm going to suggest we do here, first of all, is to subtract ln 3 from both sides. So then get that 4k equals ln 12 minus ln 3. And the same way of laws of logs, that's going to be the same as ln of 12 divided by 3. 12 divided by 3, of course, is just ln 4. So 4 lots of k is going to be ln 4. Therefore, dividing both sides by 4 now, I can see that therefore k must be, in exact value, a quarter ln 4. Let's have a look at one more example. This one I've taken from an AS past paper. So this time, again, we've used k as a positive constant, and this time we're doing the integral from 1 up to k of this expression, and we're told that's going to be equal to 4. For part A, given this information, we need to show that 3k minus 5 root k minus 12 equals 0. And then using that, we can solve B. So first of all, part A. So if I just take this, again, ignoring the limits of integration for now, and just consider what this is in a simpler way. So I've got 5 all over 2 root x plus 3 with respect to x. That's the same, partitioning it out, 5 over 2, or 2.5 is just a constant. So I'm going to say that's 5 over 2 on the outside. Root x, 1 over root x rather, is the same as x to the minus a half. And of course, if I integrate 3, that's just going to give me 3x. Of course, plus for c. So if I now were to slightly neaten this up, so 5 over 2, x to the minus a half, I'm going to add 1 to the power, which becomes a half. But then, of course, you divide by the new power, so I'm going to divide that by the half, then plus 3x plus c. So 5 over 2 times this. Basically, if you're dividing by a half, I would think of that as the same as you timesing by 2. So 5 divided by 2 times by 2, I'm just going to get 5x to the positive a half plus 3x plus c. So then, therefore, you can make space for d over here. So using this, we can therefore say that the integral from k to 1 of this thing here, 5 over 2 root x plus 3 with respect to x, is going to be this thing here, in between the limits of k and 1. Now, x to the half, because we've now integrated this, I can put this back in terms of a third. So I'm going to put this back as 5 root x plus 3x. And of course, when we're doing the definite integral, we don't need the constant of integration in between k and 1. And we're told that that's going to be 4. So let's work this out first. So the upper limit, k, that's going to give us 5 root k plus 3x, which will be 3k. Then minus the lower limit. When x is 1, 5 times root x becomes 5 times the square root of 1, which is just 5. And then when x is 1, 3 times 1 is just 3. So then nicking this up, I've got 5 root k plus 3k. 5 plus 3 is 8, so it's minus 8. And we're told as well that that needs to be equal to 4. So then finally, well not finally, just remember that's equal to 4. We're pretty much home and dry. Just one final step and we've got to what we need to prove. If I now subtract 4 from both sides, I'll therefore see that 5 times the square root of k, in fact I'll put it into the order the question's wanting. So it wants 3k first, so let's write it as the question wants. So I've got 3k, then plus 5 lots of root k, minus 8 minus another 4 gives minus 12, then equals 0 as required. So we've shown that it holds true. We've used standard results and shown working to arrive at what the examiner wanted us to prove. So that's fine. Part A is actually the hardest part. Part B is actually slightly easier. Part B, it says hence, massive word hence, not in, I know it's only 5 letters, but massive in terms of its meaning. Hence will mean use the previous part or parts of the question. So using part A to help you, and algebra, find any values of k, that's a clue that there might be more than one value, such that the integral of k to 1 of this equals 4. Well, it says hence, so this thing here, we actually worked out from this that that equaled 5 root k plus 3k minus 8, which then of course rearranged to this. So it's just essentially finishing off what we started in part A. So what we're going to do now is essentially just solve this. So we've got 3k plus 5 root k minus 12 equals 0. And I love this question because it's mixing together different skills now. How are we going to solve this? Well, we need to remember it's a hidden quadratic. Sometimes called a disguised quadratic. It depends where you're taught and who's teaching you. I tend to say these are hidden quadratics. You can spot when it's hidden quadratic if the highest power is double the lower power. So essentially, root k is k to the half. K on its own means k to the 1. A half is obviously half of 1, therefore this is a hidden quadratic. So what I'm going to say here is, let's say that root k equals big X. So using that substitution, if root k is x, then k must be that x squared. So we've got 3 lots of x squared plus 5 lots of normal x minus 12 equals 0. Now you can solve this by factorizing or using the calculator. It normally doesn't matter, but because here it's saying using algebra, let's do it the pure way. So let's see if this will factorize. So the way I factorize, going back to GCSE, you might find quite strange. Ignore this method if you wish, as long as you can factorize it and get to the same result. I don't really mind, nor will the examiner. So in terms of factorizing this, I'll now basically take the 3, multiply by the minus 12, and make this into minus 36. So I've got x squared plus 5x, put inverted brackets because it's not really this, equals 0. I then solve this in the standard way by just thinking of two numbers that multiply to negative 36 and add up to 5. And so the two numbers that will sort that will be a 9 and a negative 4. It's got x plus 9, x minus 4 equals 0. However, that 3, we need to remember that did exist. So using my strange technique here, which I think is really quick if you get around it, you get your head around it being so strange, put the 3 underneath, and then if the fractions can simplify, do so. So 9 over 3, of course, becomes just 3, because 9 divided by 3 is 3. And this one here, if you can't simplify the fraction and a denominator still remains, you just shove the remaining denominator in front of the x in the bracket. So that becomes now 3x minus 4 equals 0. And so therefore, we're trying to solve now the values of x. So for this bracket, we can say that therefore x, big X equals minus 3, or big X, if this bracket were to be equal to 0, 3x minus 4 would equal 0. X would have to be equal to 4/3. But of course, big X was actually the square root of k. So either the square root of k is minus 3, or the square root of k is going to be 4 over 3. At this point, we need to think about which options, if any, are actually valid. So, can you square root a number and it gets a negative? In further maths, yes, but for standard A level, no. So what we need to do is reject this one here. So it must be that the square root of k equals 4/3, because you can square root a number and get a positive result. But we don't want the square root of k, we want the actual value of k itself. So if we just square both sides to get what k is, therefore k must be root k all squared, which will be 4 over 3 all squared. 4 squared is 16, 3 squared is 9. And so k would have to be 16 over 9, and that's the only option we have. So welcome into the world of integration, into the deep end. So I hope you found that useful to an extent. What you will find more useful is trying some of these yourselves. Practice, practice, practice. So in the book, exercise 11a, page 295, I would tend to probably skip past question 1, just do question 2 onwards, as many as you can. If you get stuck, you know what to do. Please find me, leave a comment, or email, whichever you can, but don't leave it thinking that the problems will be resolved by not actually tackling them head on. Thank you for listening, take care of yourselves, and I hope to see you all soon.